Okay, we're going to look back at everyone's favorite antibiotic scenario and know that it can be done as a classical probability Venn diagram probability. And so this was the scenario where we had antibiotic A that was known to cure 60% of the time, but it was and only cost $50 versus antibiotic B that cured 90% of the time, but cost $80. And we were working for a health insurance company trying to determine what they recommend. And plan one was treat with A first. If not, then treat with B. Plan two was B first. If not, treat with A. And we were supposed to compute the expected cost. Well, one of the things that they told us was that the antibiotics worked independently. So let's see about setting up a Venn diagram. So here's the Venn diagram I set up with, and here's how I did that. They said the probability of A works, probability of A is 0.60, and the probability of B equals 0.90. Well, they told me they were independent, and remember, now this is only true if they're independent, so I can take the probability of A and B equals the probability of A times the probability of B. So I can go 0.6 times 0.9, and that gives me 0.54. So that's my intersection, that's my overlap. So my overlap is 0.54, but drug A works a total of 60% of the time. That means it works 6% of the time when drug B doesn't work. So, because this has to add up to my original 0.60. This side over here also has to add up to my original 0.90, because drug B works 90% of the time. So 90 minus the 0.54 equals a 0.36. I should probably go ahead and write that down, because that might help some people out to understand. This came from 0.60 minus the 0.54 equals this. And this is 0.90 minus the 0.54 equals this. And that was just purely my overlap between the two. All right, so when I look at that, it's like, you know what, it doesn't matter which way we go, we're going to get the same intersection, we're going to get the same cure rate. That's not a surprise. But what happened, because this is exactly the same as what we did before. And basically we're saying the probability of A union B equals A plus B minus the intersection. So 0.6 plus 0.9 minus the intersection. And remember, we have to subtract out this part because it got counted twice. It got counted once when we considered part A, and then it got counted a second time when we considered part B. So that's why we had to subtract it out. Now, when we look at it this way, instead of A union B, we're going to go B union A. So that's 0.9 plus 0.6 minus the intersection. And we get 0.96. It's like, oh, that's not a big surprise. Cost is where things start to look a little differently. And what that says is 60% of the time, we're going to do drug A only. But 40% of the time, I'm going to have to do both. You're like, wait a second, both. So 60% of the time, I only have to spend the $50. 40% of the time, and where did I get that value? That value, the $90, was the 50 plus the 80. So 40% of the time, I'm going to have to spend $130. All right. Alternatively, 90% of the time, I'm going to have to spend $80 only. 10% of the time, I'm going to have to spend 0.10 times the 130. I'll have to spend $130. And that would be 72 plus 130. So in both cases, if I have to buy both drugs, I'm going to spend $130. Here I have to spend $130, and here I have to spend $130. The difference is 10% of the time I spend $130 on this treatment protocol. 40% of the time I do it on this one. However, because of the initial cost differences, treatment one ends up being cheaper. Gives you the same answer. You don't need to know how to do it both ways, but I wanted to show you that you could solve that problem using a Venn diagram and classical probability. Once again, A union B, drug A plus drug B minus the overlap gave us the cure rate. Okay, all righty. Thank you for that.